is N. So if we have 5 orders, we have 250 days, working days per year. So 250 divided by 5. That means we have 50 days between each order. We learned how to calculate the setup time, total time. And then we moved to, we also talked about the reorder point, which is equal to DL. D is the daily demand, we said. L is the lead time. We solved several examples last time. And then we started the production order quantity model. And we said we use it when we have inventory builds up over a period of time. So we are producing here, we have production. And we generated the equation for the Q star with P, we said that's the equation. So the equation is this. So Q star P is equal to 2ds over H1 minus D over P. And we had one example. We solved this example. We were asked to calculate Q star P. We said we use, for this example, we have forecast forward. This is the demand, an average daily demand for units. However, the production, see, when you have production involved, so you need to use this equation. So 2ds over H times 1 minus D over P, and this will give us the, that's what we did last time here. We stopped here. Okay. D over 4, so D equal to 4 because D over the 250 days, D is the annual demand. If you divide the annual demand, as we said, divide by 250, this will be equal to 4. This is the daily demand, okay? This is called daily demand, okay? Daily demand. When annual data are used in the equation, you know, we can change the equation and we can use 1 minus the annual demand rate divided by the annual production rate times H under the square root times 2ds, and this will give us the P star again. Okay. The other model is the quantity discount model. So we have the EOQ, we have the EOQ, and we have the quantity discount model and the production model. So we covered the production model and the EOQ. Now we are going over the discounted model. So when we have reduced prices or discounts available for, of course, larger quantities, we use the discount. So for example, here, this example here, we have the quantity from 0 to 119, the price is 100. But if we buy 1500 or over, the price will be, for example, 96. This is the discounted. Like when they say if you buy a case of Coca-Cola, the price will be $6, for example. But when you buy one bottle, it is like $2.99, right? That's the discount for quantities. Again, we can come up with the equation. The total cost is equal to the setup cost divided by plus or holding cost plus the product cost. So Q is quantity ordered always. D is the annual demand always. S is the setup cost. Okay. P is the price per unit here. That's what we added. And I is the holding cost per year expressed as percentage of P. Okay. So we know the 2DS, right? In the beginning for the first model, the EQ, we said Q star is equal to the 2DS over H under the square root. Then we said for the production unit production, it is equal to 2DS divided by 1 minus D over P times H. Now we have I as holding cost per unit per year it is involved because unit price vary. That's why we have I, because the unit price vary. It is changed, depends on the quantity. Okay, these are the steps in analyzing the quantity discount. Starting with the lowest possible price, calculates Q star until the first visible EOQ is found. This is a possible best order quantity along with the price break. Calculate the total annual cost for each possible order, and then select the quantity that's it. You are given different prices, different quantities. Start with the lowest possible price and see if it is visible. We will see what's visible means, makes sense, meets all the requirements, that's visible. And then we calculate the total cost. Okay, let's look here at this example. So discount price 1, discount price 2. So discount price 1, if you buy between 190 and 1499, which is below the 1500 here, okay? Anything here is visible, anything here is visible. So if your quantity, if you are using this price and you came up with a quantity between 120 and 1499, so it's visible, you got the discount. But if your quantity came up here, so it's not visible. If it is here, it's not visible. and the same thing for the second price. Let's see this example here. A typical quantity discount schedule appears in table 12.2. As can be seen in the table, the normal price of the item is $100. When 120 to 14.99 units are ordered at one time, at once, the price per unit drops to 98. So they drop the price for you to 98. When the quantity ordered is above 1500, the price also drops to 96. The 120 quantity and 15 are called price break quantities because they present the first order amount that would lead to a new lower price. The price break quantities, these 20, 120 to 14.99, because they represent the first price with discount, okay? Or lower price. As always, management must decide when and how much to order. However, given these quantities discount, how managers make these decisions, we need to decide which one to take, this or this or this. Okay, let's start. Based on the procedure, we said we start with the lowest possible price, and then we see if it is feasible. So this is the best price, this is the best solution. If it is not feasible, we go to the next price. Then we go to the following one. Okay, so how we start? Calculate Q star for each discounted or discount starting with the lowest price using the formula, which is this formula, 2ds over IP. So the D is given, which is 5200. S is also given, 200. So 2 times 5200 times 200 divided by I, which is given, times the price, which is P. We select first the 96, okay? So the 96, then we get the Q for 96 price, the Q star for 96 price. So to get this discount, every order should be 278 hadrons. That's not feasible because it says here to get the 96 price, you have to order 1500. You see? That's why it's not feasible. That's not feasible. Okay? Then we calculate Q star for the next higher price, which is 98. 2 times 5200 times 200 divided by 0.28 times 98 now. See, we just changed the price. It's 275. Oh, 275 is here. It is between the 120 and 14.99, right? You have 120 here, and where you have 14.99. So our 275 is in the middle here. So it is feasible. So this is our best price. Okay? Questions? Any questions? By the way, some of you, let me go back to the class website, asked me to post the meeting we did last time, and I did same day, but I think nobody watched that recording. Let me see. Here, I posted this. Yeah, and I think nobody watched it. See that nobody watched it. This is our last week lecture. If you go again, go to home page, click here, and then you should be able to find that recording of last week, this week. And I will put the recording for today's lecture here behind under this. And we will have a test soon. We will be having tests soon, okay? So we will be having tests soon. Test 2. Test 1 practice test I already posted. So we'll be having the test probably on March 27, probably. I will check again and see. I will let you know when the test. So if we say March 27, so let's bring the calendar. Oh, March 27 will be the next week, next Thursday. Oh, we might make it April 1st, okay? We might make it April 1st. Let's see.
Will it be in person?
I don't know. I will let you know.
Okay.
We will see. Okay, this is how we decide which price works with us. This is another example here. We start with the lowest price and then we decide if it is feasible or not. There is another method called probabilistic from probability, probabilistic model and safety stock. ROP is equal to D times L plus SS. SS is the safety stock. Annual stock are the sum of the units short for each demand level times the probability that the demand level, the stock out units, the number of orders per year. So David Rivera Optical has determined that the reorder point for eyeglass frame is 50. Okay, this is the reorder point. It is carrying cost per frame per year is $5. That's is the cost for carrying each eyeglass. And stock out or lost sale. See, this is the difference. Lost sale cost $40. If they lose a sale, like how do they lose a sale? That somebody come and say, oh, I want this eyeglass, and they don't have it. So that means they will lose $40, okay? The store has experienced the following probability distribution for inventory demand during the lead time. The optimum number of orders per year is given 6. Okay. This is the ROP, reorder point. Orders per year 6, stock out cost 40, carrying cost 5 per year. Okay. Number of units that will be sold if the probability of selling 30 is 20%. The probability of selling 40 is 20%. The probability of selling 50 is 30%. The probability of selling 60 is 20%. Probability of selling 70 is 0.1% or 10%. This should add up to 100%. So if you have one missing, you should subtract the total from 1. This will give you the missing probability, okay? We know that. Okay. So safety stock is 20. 20 times 5, because holding each unit will cost us $5. So 20 times 5 is 100. Stock out cost, no stock out. So we have everything in this case. We have met all the demands. Nobody came and we said, no, we don't have. So we didn't lose. So the total cost will be 100 if we have 20. But if we have 10, so holding the 10, keeping the 10 glasses in our store will cost us $50. 10 times 5, 10 glasses times $5, $50. Okay. And look at the table here. Look at the table. 10 times 0.1, right? 10 times 0.1. 10 times 0.1 times 40 times 6. 6 orders. Okay. 240. So the total cost is 290. If we have zero inventory, 10 times 0.2 times 40 times 6 plus 20 times 0.1, 10, 20.1. You see? So it's 960. Safety stock 20 frame gives the lowest total cost, which is 100. There is another example here. Oh, I put this extra example because there is a question, or this is a question from the person, my lab. Do you demand during lead time for one brand of TV is normally distributed with a mean of 36 TVs and standard deviation of 15? What safety stock should be carried for Denise U appliances outlet to provide 90% service level? What appropriate reorder point? Okay. Yeah, this is, I think, example from the book. I will go to the book and do it, but we CS cost of shortage, CO cost of average. Okay, the service level, that is the probability of not stocking out, is set as service level. You see, we are given here the service. Yes, that's so. Let's go to the book and see the example from the book. Yeah, I should put the uh, page number here. See, this is our textbook I'm using. I'm just trying to find it. This is the cycle counting, which we did. So when you study for the test, you need to use the book, definitely, not just the PowerPoint. Inventory models, holding cost, definitions. That's the EOQ model here. The reorder point. This is the production quantity model, which we just covered. The discount. Oh, here is the example. You see this example, page 514. Let me put page. So next time. Okay. CS cost of shortage, we did that sales price minus cost of per unit. That's how it costs you when you have shortage, right? If you sell something for $100 and it costs you 50, so you are making $50. So if you don't sell something, if you have shortage, you will lose $50. Cost of average, we overestimated. Cost per unit minus salvage, sometimes you. So service level is equal to CS divided by CS plus CO, okay? We should consider increasing our order quantity until the service level is equal to more than the ratio. Okay, this is an example here. So Chris Ellis, just outside the Smithsonian subway station in Washington, D.C., usually sells 12 copies or 120 copies of the Washington Post each day. Chris believes that the sale of the Post normally distributed with a standard deviation of 15 papers. He pays 70% for each paper, which sells 125. The Post gives him 30 cents for each unsold paper. He wants to determine how many papers he should order each day and the stock out risk for the quantity. So the CS is cost of shortage, is how much he sells the paper, 125, minus how much it cost him, 70 cents, so 0.55. CO, cost of average, is, you see he, at the end of the day, he will get rid of them at 30 cents. So 70 minus 30, he will lose 40 cents for each one. Okay, Chris will apply equations and the normal using mu. We have a mu, which is 120 here. And sigma, it's given 15, right? 15 papers. So the service level is 0.5 divided by 0.55 plus 0.4, it's 0.579. Chris needs to find the z-score for this normal distribution that yields the 0.579. Okay, so the z-score for this is 1.199. I can use, you remember the tables I gave you? Let me see which chapter. Normal tables, these are the factor tables. I gave you copies of those normal tables. Okay, so we said how much was the 0.579, 0.579. So we need to look here for 0.579, 0.5671, 0.579 here. 3. But it was 0.57. So it is between 0.199 or 0.29. So they found it as 0.199. Okay. So then the optimal stock level is equal to, we use this equation, 120 plus the Z times sigma. Okay. Z plus sigma. Let me copy this. Originally we said Z equal X minus mu divided by sigma, right? If you cross multiply, Z sigma equal X minus mu. Okay. So if you take this X to this side and Z sigma to this side, okay. So now you will have X equal to mu minus or plus, because this will be negative, so you multiply everything with negative, so you will have mu plus Z times sigma. So X is the optimal stock level that we will need, is equal to the average plus the Z value times sigma. Okay. If you know sigma and you know the average, you need to find Z and multiply it by sigma and add it to the average. For you provide 90% service level. So here in this example, let me look at this example here. So with a mean of 36 and standard deviation, so X is equal to, as we said, 36 plus Z times 15. How do we find Z in this case? We are given 90%. So the same thing, I go to the table and find the Z for 90%. It's 1.2. It's 1.285.